Figured I'd go ahead and just get started because I have a lot of ground to cover. So I'm going to start with basically quantum computers. And we can encode, you know, pairs of zeros together. 0R, these are real zeros. And then we could have 0R with a with an imaginary one. Just make it an I. And then you could also pair this with that. I'm just trying to make it a little bit more standardized. Yeah. Here's imaginary over there. And then just pair the real with the imaginary. So we can kind of get these three interactions going on. And this is the imaginary. So this leads to the idea that you know we can encode curvature into the O fields. The O fields. And there's a few different types of them, I guess. So this is essentially the quantum fields. And we can pair interactions into three forms. These three, one, two, three forms. And so we have the three form. Of course, you could just focus on one of them by themselves, and you'd kind of have like a one form for it. So like this particular interaction set could have a one form. This could have a one form. This could have a one form. And then you kind of put them all three into this three form. What that means is we're just taking derivatives of these. You kind of have different dimensions for them. So theoretically, uh, back in our model of the quantum gravity system, we had some 2D areas appearing. So the idea is you can potentially even make 2D areas out of this. But let's see, so the field that's imaginary could be represented like this stuff right here. In fact, that 2D imaginary field is essentially a two form. So there's your two form. Here's the two form. So you can get like a 2D surface area. Okay. Now, we could keep going. So a four form emerges from here because we have a three form, which can give us three dimensions. And then this is all embedded in a system of time. So we have this modular time situation. So there's this three form embedded in time because we had this time axis that we're sort of folding up essentially and connecting in different ways and spinning around. And so we have um, three different ways we can spin it, and that leads to a three-form volume essentially that's embedded in this time thing. It's a modular time, so we have this t, which is modular, and of course that gives us the 3D embedded in this modular time, if we could say. Although in our case, usually we focus only on real time, because let's consider that there's also a 5 form. We should consider that 3D real volume, but that time dimension has t plus imaginary t. So let's not forget that. All right, go ahead and label this like that, I guess. But the 5 form isn't quite complete yet because we've only considered the real 3D over here. And then what we're just going to add in the imaginary time and hope that works out. Well, technically we should be adding even more to this. So we can get a 6 form where you have X star, Y star, Z star, and these are essentially complex coordinates. So consider that it's going to be A plus BI, and you would have this in 3 dimensions. So you can, these are complex coordinates, and yeah, you kind of have like, this whole situation. This is all like in a complex plane, I guess. So you have this um, 3D complex, which turns into this 6 form volume. Alright, so we're stacking dimensions up here. We're just seeing how more and more of them appear, but you see they're all just linear combinations of each other. It's not like we're just like different types of combinations of each other. We're not just like coming up with random letters. Okay, so we have the 6 form, the 7 form. How do we get the 7 form? Well, we didn't even include time in this 3 form, did we? So let's put that in there. So we should be looking at something like X, Y, Z, uh, I'll call it T, X, Y, Z, T, and then we have this. So this is our 7 form. We combine that together. I guess it makes more sense to put T on the other side. This why not too much. Go like that. 1, 2, 3. Put the T here. T, X, Y, Z. And then we have over here. We can. Oh well. We'll wait on that. Wait on that. First, throw these forms together, and then we can get an 8 form going. But really, this 7 form is supposed to be more to see a combination of a 4 form and a three-form Hodge dual, or it's really a seven-form Hodge dual. Just the seventh form is that whole combination here, and the three form is here. The seventh form is the Hodge dual, and so we have the fourth form. The three form is yeah, you could say something like this. So you kind of have like a four form and a three form, which allows you to get this Hodge dual setup going on. Um, now, we're still not there yet because close. Let's if, let's get the complete form. We get to the eight form. Maybe we don't really need an eight form. Really, what's happening here is in order to get the four form and the seven form Hodge dual, you had to have TXYZ, which is a four form, and then you have this other four form, and then you have well, you take some combinations of those three so you can link them in a certain way. A, B, C, or something. And it turns out that these are essentially the interaction groups, gauge groups. So like you have U1, SU2, and SU3 forms. So here are your gauge interactions. This means is kind of like which combination are you going to take of these three, put them in its own little form over here, and then you've got this form right here, and then you have this form right here. Usually we tend to interact the gauge interactions only with the real side, but we should be able to interact it with any form. And so this allows you to sort of get 11 dimensions out of this, because you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. So there's essentially a lot of stuff. Yeah, even though this thing you would consider is like a repetition, don't forget that these guys are supposed to be A plus BI, and there's like three of them. So that gives you a lot. But let me just go ahead and just in case. Just kind of gives you a very, very wide range of options on how you can sort of combine all these different derivatives. General relativity is just this one right here. Alright, so this is kind of cool. This is how the forms interact together. And I wanted to sort of put up some axioms as well, some ideas, and see if these hold. So all quantum info is encoded in zeros and ones. Is essentially how this can sort of work. Um, because the zeros are going to be the nodes, and the ones are essentially the axes that we have to cross. I mean, it's basically the idea. Now, that's kind of very limiting, but it's very powerful as well. This gives us the ability to have superposition and entanglement. Because, well, zero could be here, but zero is also here. Zero is here as well. Anyway, we'll see how this continues. Essentially, these ones are going to be the energies, and the zeros are the voids. And you're able to combine the voids and the energies by using, say, alpha energy, or alpha void, in this case of alpha zero, and beta void, beta energy, or so. So you can sort of actually get a superposition and entanglement of these two combinations. Um, Zeros, interesting, because we have imaginaries and reals. And apparently, as far as things seem to be going, real zeros are actually going to be Higgs bosons, and they produce the Higgs field. Whereas the imaginary zeros are essentially the gravitons, which produce the imaginary volume. It's a complex plane. So that could be so maybe imaginary. This is the gravitons, and they seem to exist in the complex plane. Okay. Um, and this is actually apparently dark matter because it's causing curvature. Both of these things are encoding curvature. But the difference is that the Higgs field affects real curvature and the gravitons affect complex curvature. And so therefore, dark matter is simply complex particles that don't interact with the real plane. We have a lot of evidence for this dark matter, and it doesn't interact with this plane in any way. Well, it does in the complex plane. The complex plane, it interacts in some ways, obviously, because you have to, but it doesn't interact with like if you just take the gauge interactions here and then just use that, you're not gonna get you're not gonna get the correct calculations. You try to use just the curvature from the Higgs field, just general relativity. You're gonna need the curvature from uh, the dark matter field as well. So that's basically giving you our our issues there. Um, so what's interesting is that everything else, everything here has mass, everything here has no mass. But this is in zero form. So things can also become the energy form, the one form. It's usually like one times energy because you want to have some energy at that one. Obviously here you have no energy, but the energy value is still there. Let's not take away that energy value because we know that zero does have energy. I believe that would be dark energy. So it's possible that this is even dark energy emerging at the moment. You never really know what's happening here. So we'll just go ahead and leave this as sort of like a question mark maybe. Is this the dark energy? I don't know. Where's the dark energy? I don't know. We'll have to come back to that later. But for now, let's figure out what we have. Figure out what we have. Energy flow is always continuous. Energy flow is, well, continuous. Although it seems to be sort of maybe breaking itself, but not really. Because the problem is we can't really just go down this line here. We have zeros along the way. So we have to kind of do some little bizarre stuff in order to get around these zeros. Energy has to sort of appear here and then turn into zero. Really, what's a better description is maybe trying to shoot a zero across here and track the path of like this zero as it's going through here and then sort of connecting to that zero and then sort of following this little path down this curved line. This is sort of the path of the energy flow. Energy flow. And it's kind of like, you don't really know where that energy is going to appear, but there is a probability that it will appear at certain points. So you get this distribution. And this is in fact the wave function. But as you can see, it kind of does this. If you want to get the amplitude, you want to square it. That'll give you something a little bit more reasonable to work with. Because then you get something that looks more like this. Okay. So that each one of these are kind of like discrete wave function packets that have to um that have to materialize at each particular point along this axis, as it sort of slides down this axis. Of course, you could have curvature in the axis, which would affect the probability distributions. So consider that curvature means the probability is going to be changed. And this is, in fact, the gravitational effects that gravity is going to have on the wave function. It'll just simply affect the probability. Curvature of probability will sort of be along this axis. You can imagine there's like a little bit of curvature here, which will definitely cause this path not to be particularly straight. But the energy is following this straight path. Well, it has to it has to pass through these voids. The zero energy points. Well, how the heck is zero going to be able to go from this to that to that to that? It has to do this little Fourier transform. So we're doing a Fourier right here. And we're materializing as basically halves, ones. We're materializing this void of energy as something there, and then all of a sudden back to this void. And so it just kind of blips in and out of existence. And usually it's going to follow that general straight path, you could see. But the curvature will affect the probability distributions here. So okay. It's kind of interesting. And essentially we have at each one of these points a wave function collapse. And that's going to be the green thing. Let's just call it a collapse. Okay, so stuff materializes, basically immaterializes the materializes, immaterializes the materializes. Tunnel is dug along the diameter of Earth, a particle mass m, or is the radius of the Earth, m is the mass of the Earth. Hell yeah, find velocity. Well, that's kind of a regular problem, which sounds definitely pretty interesting um, and difficult. But at the moment, I have to continue quantizing gravity, otherwise civilization is going to fail. But I want to take us to that next type. So let's go ahead and try to get this done here real quick. Anyway, the idea here is that all quantum activity all quantum activity resolves before the next tick. So basically, this is a tick of time right here. And fittingly, there is actually an imaginary axis coming out of here. I'll just put that here. So the imaginary axis popping out at each one of these little ticks of time. And, well, let's reflect the curvature a little bit too. You can see it's kind of curving. I don't know where it's going, but I'm going to curve too much. This imaginary plane out here is tangent in all directions, so we kind of have this, literally it's this screen, holographic screen that you can sort of see appearing here. 3D area, or a 2D thing, you can make it a 3D area. There's so many ways you can connect this, but essentially you have this thing here. That is in fact all the quantum information, the quantum activity, happening in the imaginary plane. That's the quantum activity. And that stuff has to resolve before passing to the next tick. And it's going to resolve that by being able to sort of uh, quantum tunnel along this little path and sort of materialize here and then immaterialize. In order for that to happen, it has to quantum tunnel. Oh my god. Well, we note that as sort of a red, perhaps. Quantum tunneling of information. And where did it happen to appear? In this case, we materialized it here, although it could have materialized over there. But this is, in fact, there. That might be more of a better representation of the collapse happening at this point. If we consider this to be a wormhole, good God, a wormhole, wormhole causes the wave function to collapse. And at that particular point where it's like, well, let's not forget there's supposed to be more stuff on the other side too, right? It's like all this possible stuff here. There's much more on the other side. So, you gotta get this shape for me. There we go. That's much better. So that way you can see, yeah, it would make sense for it to materialize right about there. You have this wormhole that allows you to tunnel and collapse the wave function right here. And what happens is the Fourier materializes, and what we have done is we have turned a 0 to a 1. And that happens through the Fourier transform. So you have to take an integral of 0 and then all those possibilities and select one of them. And that ends up being sort of your value that you can pop up right here. It sort of allows you to be either a 1/2, -1/2, a 1, a 0, and it's going to appear here. And, well, you've selected one possibility out of basically infinity. So it's like, oh my god, right? But this does require some energy. So you did get some energy out of this. Let's realize that there's a lot of spinning going on here, and here's the cool thing: is that the curl, and the div of the quantum activity, and I'll just denote that as kind of like the spinning stuff that happens, and the div is really, what gets shoved through this hole. That curl and the diving process of the quantum activity manifests into energy. where's the, yeah, the correlative, the quantum activity manifests into energy. Um, but of course, this length here that we have, this length appears to be length of h. So we still work with h, and the frequencies. I believe there's a lot of spinning happening everywhere, so it's like pick any one of those frequencies and just call it a day, right? So clearly we have that going on there. Yeah, the quantum info is essentially the frequency, whereas that length that we have there is the length of time here. So this is h right here, and there's like little h's that kind of keep going. Little h. All right, so that was about that for that page. There's a lot of stuff I have to get through, so that's why I wanted to kind of start right now. Uh, we covered the idea that dark matter causes imaginary curvature, right? Real curvature is caused by the Higgs field, so it can't interact with each other except through curvature. Yeah, those are the only two ways that these things can interact. So the curvature of this affects the curvature of that, vice versa. But that's really the only way that these guys interact. Other than that, they're just kind of spiraling around each other. And that's how you get HF. Um, so that's kind of interesting. This is in fact the curvature of each one of these individual H's. This is the real axis here. And this is the imaginary axis here. Um, so this curvature, what does it represent? This curvature represents non-realized possibilities. In fact, so where's the curvature of the non-realized possibilities? Where is it? One possibility out of infinity emerged as energy over here. We're talking the stuff we can interact in the real axis, so we'll call it real energy. And we chose one possibility. Usually that's a very small portion of the curvature. So like basically one state. That whole thing represented. That's all we can get. So apparently this is starting to manifest as like about 15% of energy happening there versus like 85% of the energy here, or really 85% of the stuff would essentially be dark matter. All the unrealized possibilities. I know it seems like a lot of energy just for one possibility, but remember, usually this stuff happens at expectancy values. So like it's a large chunk of the probability that that one possibility pulls out. And just to sort of describe this, the um the percent chance for an electron to be found at the between 0 and the Bohr radius is about 32.5% or something. And so if we just took that um, one quantum state, it would essentially be a very small but a large chunk at the same time. So it's kind of like this number kind of sucks right here. The Unfortunately, the expectancy values are kind of like weird to calculate because it's not just at that point that we're calculating. We're taking an entire integral. So what we're doing is we're basically saying like, how can I show this here? I think this is the picture for the next sort of page. Now we're gonna get into this. Yeah, let me just kind of quickly go into this here. So there's basically a 0 here, and there's a 0 here, right? But you can normalize this probability in between the zeros. And, it'll look something like that or whatever. It's about, if you measure from here to there, that's about 32.5%. So if we selected, a chunk here, and this was our energy that materialized at this point, the probability there, then we had to first of all choose this direction. It shows up here. Well, why didn't it show up right here in the middle? There's all sorts of reasons because we have an imaginary percentage, imaginary axis effectiveness, etc., etc. So this kind of gets normalized to 1. This is where that materializing happens. There's a little node here. These are nodes. And this is a node. So, we're not breaking any rules here. Usually this tends to materialize stuff that has like spin of 1/2 or -1/2 or 1. Or if you're looking at the graviton, it will materialize at a spin of 2 because it has 2 degrees of freedom. Remember that there was one real. Here's spin 1 for the one real. And 2 for the imaginary. So, let's go back to this curvature though. Curvature in the imaginary axis. Imaginary curvature, and then real energy. So this kind of gives us the real curvature. Awesome. Where do we need to go from here? Let's take a look at measuring this imaginary curvature. So we would want to alter the Einstein field equations. let's just take a look at how we can modify that. Before we do that, let's just take a look at the original Einstein field equations so we know what we're sort of expecting to see. So it's something like this. So this is RUV minus 1/2 GUV R plus this dark energy thing, GUV, is supposed to be equal to 8 pi G over C to the 4th power. I have T UV. So let's try to modify this a little bit. And the way we can do that is look at this R that we have. Let's take a sum of these R's. So we will have the real version, and then we'll have the imaginary version. Same units, no problem. Do the same thing with the energy tensor here. So we can modify this, and basically take the real one and add the imaginary one. See where we are. It's pretty easy. So fully imaginary version of EFE here. Kind of, we have forgotten this particular one. Take this and also give that one some imaginary curvature. I wait this down. Go ahead and give that some heat. Okay, so we've modified the Einstein equations to add the imaginary part. And this stuff corresponds to about 15% of the energy versus this stuff is supposed to be 85%. You know, the numbers are kind of matching up. There's a lot more stuff happening in the imaginary plane. And this can be represented, again, by the unrealized possibilities and just the idea there's just so much crap happening here before that one single second happens. And this isn't the EM field, this is actually the Higgs field. So that's pretty nice. And these guys are actually not photons, but rather Higgs. Still in there. So these things can interact with each other in different dimensions. That allows us to create this 3-1 spacetime. Interesting. All right. All right, let's continue over here into the standard model. Did I complete this page? One, two. All right, so let's rewrite this equation now, I guess, using the full versions. It's not going to be all that much different. We just plug these numbers in. Okay, so we're just going to, yeah, so we modify that by that, complexify that. And essentially, the idea is that we have the gravitational potential being equal to the real plus the imaginary. That there, gravitational potential gets adjusted by the imaginary stuff. A lot more unrealized. There's a lot more unrealized possibilities than there are realized possibilities. So, yeah. The unrealized stuff is all that information, it's gonna affect the real stuff, obviously, because I mean, it was a possibility. It was like, oh man, I could have done that, but it didn't happen. So you get kind of sad about it. It's like that opportunity never happens again, but at the same time, you're affected by the outcome. So these things affect each other, realized and the unrealized. So we're going now into what happens into the wave function collapse during the tunneling process, which is here. We have the wave function starts out, we'll call it initial, I guess, and then at the next point in time, real time, the next wave function will materialize. So you have, I'm trying to do something like this. Um, I'll have to go more into the math of that, but here's what's a little bit crazy. I'm just gonna go ahead and ignore that for now. But let's say that we go ahead and put some quantum information down this funnel. And yeah, let's say something materializes right here. Well, if that happens, it will send out some waves. These are gravity waves. Essentially, it's going to curve the axes and curve everything, so whatever. It's going to curve everything. everything gets curved. How do we do that? Well, we take our original G, yep, here. What am I doing? Whatever. Forget about all this notation. Let's not make it too complicated. Let's focus on the idea that we have an altered thing here. Um, an altered thing, and what we're going to do is add a little perturbation. And the perturbation is a function of that, some e to the I t, and quantum um, energy, energy density, the energy density of the quantum information, which is of course complex. So there's just a lot of stuff that's being encoded as the wave function collapses and sends out these little perturbations, these little gravity waves that send out at every collapse. This is again the quantum info, tunneling down here, materializing at a point, and sending out little gravity waves as it materializes. This was that Fourier transform from 0 to 1. And let's see if we can take a little derivative of the H here, this perturbation. Set that equal to 16 pi g over c to the fourth t, and this is the tensor. So this thing here, it's required a bit of energy to materialize there. It took it from the quantum realm, materialized it in the real realm, and caused a perturbation along all the axes. It's pretty legit. The reason it did this is we have a quadruple moment happening at q mu v. which is essentially the change in that quantum information density here. There's a little change in the quantum information density. That little change caused a quadrupole moment. And therefore the second derivative of that is going to be the wave, which is this thing right here. This is the second derivative. Okay. Now, it would make sense that, well, really, all we're trying to do here, all we did to try to achieve that is we tried to bring together these voids, right? We're going to have two voids, a void and a void. And we want energy to go down this way. It could go the other way, but the idea is that, like, the voids are sort of coming together. Okay. So this happens when a void approaches the void. We get this point in the middle where they join. They join, or essentially split in the middle here, or essentially tunnel from one point to the next. You have to connect them somehow. And that is exactly what is happening here, is that process is happening. We are combining the voids, splitting the voids, tunneling the voids down the axes towards each other. And these things send out little tiny microscopic gravity waves that are just so small that we can't even really feel them until a massive one happens, where those giant black holes, those are all just these huge collections of these tiny little things happening in very, very large stuff. So this is essentially um, tons of quantum info collided. All right, so that's pretty good for that one. So there's a lot of stuff. Let's see what we've got. Quantum computer encode as zeros, basically combinations of zeros, and then we have all these different forms that we can make with just those combinations of zeros, which is great. That gives us a three space-time with complex coordinates too. We have gauge interactions coming out. Uh, these gauge interactions, we'll describe them a little bit later. We have the zeros and ones connected together like that. Voids in the energies. Superposition entanglement. No mass. Mass. Uh, and then the energy flow is just going to flow from one void to the next, materializing sort of in between as the voids connect and funnel the quantum information between each other. It's going to materialize a little piece of information, but there's so many unrealized possibilities. That's essentially how we can help describe the couple of gravitational effects at the quantum level. Um, At this point, I think I'm starting to head more into the standard model, and so I think that's maybe best for another video. But at this point, we have definitely connected how quantum gravity actually, well, dark matter emerges from quantum gravity as the gravitons in the imaginary plane. And it connects and it creates curvature in all the axes. Curvature, and well, considering that curvature is the only way that the imaginary and the real can interact, um, that makes sense that that's the only way they can interact. They don't get really a gauge group in our real axes. We'd have to basically maybe calculate that in some other way in order to sort of get the correct information about the curvature. Once all the information about the curvature can be calculated using the imaginary axes, it's more likely to make better predictions about the dark matter curvature, just purely based off of the, well, a little bit of modified general relativity. We should be able to calculate all that curvature. All right, so anyway, I think this is a pretty good time to call it a day.